Good day, everyone. In this series, we'll be solving a few questions in physical electronics. And here we have our first question in this question bank. So here we are meant to show that the first time derivative of the expectation value of the product of the position and the momentum of a microscopic particle with same mass m in a three-dimensional space is given by ddt of the expectation value of x dot p being the same as the expectation value of the momentum squared divided by the mass minus the expectation value of the position times lambda v, where v is the potential operator. Good. So let's begin. Now, to derive the expression for d dt, the expectation value s dot p, we already know that the Hamiltonian is given as a sum of the kinetic energy and the potential energy. And to begin, we need to compute the commutation, compute the commutator, quantum bracket of the product of the expectation and the position and the Hamiltonian. So we need to resolve this to begin. Now, since the particle is in three dimensions, let's put that down. Since the particle is in three-dimensional space, then the expression of the product, that is expression for the product of the position and the momentum will become s dot p being the sum, taking values say from k, from 1 to 3 being the dimensional space, then s sub k, p sub k. So if this is defined, then the Hamiltonian, then the Hamiltonian in terms of the particle in three-dimensional space will become h, which is the Hamiltonian, will be the same as 1 over 2m, which is a constant, sigma k, taking on value from 1 to 3, then p sub k, which is the momentum squared, which is the potential operator or energy, plus the potential energy. So now that we have been able to represent the product and the Hamiltonian in the three-dimensional space, then we can go on to solve the commutator, which is the quantum bracket of the product and the Hamiltonian. Okay. So since we have to evaluate the commutator as the PH now by using the linearity property, also the properties of the commutator, we may expand this as the quantum bracket between the product and the Hamiltonian will be the same as the values in the three-dimensional space, taking k taking on value or values from 1 to 3, s of k, which is the product, p sub k, comma, which is the product of the position and momentum, and then the Hamiltonian to n sigma, let's say take L, taking on value from 1 to 3, plus the kinetic energy, p squared, then plus the same operation, which is the product, k equal to 1 to 3, s of k, p sub k, then, excuse me, the potential energy. Now recall, this plus this gives us the Hamiltonian. So should we spread this all out, then we now have to take the commutator between the product and the potential, and the potential energy, and the commutator between the product and the kinetic energy. And so, for ease of analysis, let's resolve the two components, the two components on the right-hand side separately, or 10 by 10. So we want to resolve this first, and then we resolve this next, then we'll add them all up together, their results. So, to evaluate the component with the kinetic energy, then we have that sigma k taking on values from 1 to 3, s of k, p sub k, 1 over 2m, sigma L equal to 1 to 3, p sub L squared. So now you want to recall the commutator properties. So let's recall. So, properties where the quantum bracket between the product of two operators and the third operator is given as A times the quantum bracket between B, C, plus the quantum bracket between A, C times the B operator. And also, we equally have that the quantum bracket between the position and the momentum is the same as J H cross delta KL. Okay. So now that we have this, then we could evoke all of these into this expression, and then we begin. So hence, we now have that we now have that quantum bracket with summation K equal to 1 to 3, likely because this particle is in 3-dimensional space. Let's put it that way. Then piece of K, 1 over 2n, sigma L equal to 1 to 3, piece of L squared. We now do. So after resolving the commutator between the product and the kinetic energy, then we now resolve the commutator between the product and the potential energy. So this would be the same as 1 over 2n, which is a constant, sigma K equal to 1 to 3, then sigma L equal to 1 to 3. Then we have S of K times, going by the properties, piece of K, piece of L squared, plus S of K, piece of L squared, times piece of K. Now, since we also were able to establish that piece of K, piece of L squared, the quantum bracket, is the same as 2 piece of L times the quantum bracket between piece of K, piece of L, then this would be the same as 2 piece of K, J, which is the complex quantity operator, then H cross, which is the reduced time constant, times delta KL, then the same as S of K into bracket, quantum bracket, piece of K, piece of L squared, to be the same as S of K, 2 piece of L, J, H cross, delta piece of L, which is the same as 2J, H cross, S of K, piece of K. And then we now have that S of K, piece of L squared, is the same as S of K, piece of L, which will be the same as piece of L, S of K, piece of L, plus S of K, piece of L, will be the same as P sub L, J, H cross, delta KL, plus J, H cross, delta KL, PL. And this is going to be the same as 2J, H cross P sub K. Hence, we now have that sigma K taking on values from 1 to 3, S of K, P sub K, comma, that is the quantum bracket between the product and then the kinetic energy, sigma L equal to 1 to 3 PL squared will now be the same as 1 over 2m into bracket sigma K equal to 1 to 3 2j H cross S of K P sub K plus sigma K equal to 1 to 3 2j H cross PK H cross P sub K, and this will be the same as J H cross over M. So this will truncate this, will truncate this. So we have JH cross in common, JH cross in common divided by M. Then, and then we have PK. So it's will be the same as 1. So hence, the quantum bracket between the product between the position and the momentum and the potential and the kinetic energy to P squared divided by 2m will be the same as J H cross P squared. Yes. P squared over m. And then the next thing to do would be to evaluate the component with the potential energy. And we have that the quantum bracket between the sigma, given this taking on values from 1 to 3, S of K, P sub K, and the potential energy. And then by, let's say, by applying the product rule for Commutator, and based on the fact that, the quantum bracket between the momentum and the potential energy is the same as negative JH cross dV the x of k, then we have the sigma k taking on values from 1 to 3, S of k, P sub k, then the potential energy will be the same as sigma k taking on values from 1 to 3, S of k times the quantum bracket between the momentum and the potential energy. This will be the same as sigma k equal to 1, 3, S of k minus j h cross dv dx of k, which will be the same as negative j h cross sigma k taking on values from 1 to 3, then S of k dv dx of k. So now that we have this expression also, then we can combine this expression and this expression. This expression is the result of the commutator between the product and the kinetic energy, while this result here is the result of the commutator between the product and the potential energy. Now, having solved this separately, then we now have that or let's say, let's put this in a more appropriate term, say by combining the results from the separate analysis, we have that S of P as a commutator between the product of the position and momentum and the Hamiltonian will be the same as J H cross K squared over M minus J H cross sigma K taking on values from 1 to 3 S of K dv dx of K. Now, recall we have to evaluate the first time derivative, okay, of the product. But to evaluate the first time derivative, of the expectation value of the product of the position and the momentum. Recall that the first time derivative of the expectation value of an operator is the same as 1 over JH cross the expectation value of the commutator between that operator and the Hamiltonian plus the expectation value of the partial derivative of that operator with respect to time. So going by this, then we can now say that for the product which is time derivative or time dependent rather, is time dependent, we now give us this. such that the first time derivative of the expectation value of the product of the position and the momentum will therefore be the same as 1 over JH cross, and the expectation value of the commutator between the product and the Hamiltonian will now give us 1 over JH cross. Then the expectation value, we already resolved this, JH cross P squared over M minus JH cross sigma K, taking on values from 1, 3, S of K, dv the S of K, this. And once we strike this through, then what we have, now this is going to give us Nambla V, why this is S of K, and then this is going to give us P squared over N. And once we take the expectation value, then we have a negative here. So this is going to give us the final answer, which is D, the T is the same as the expectation value between the ratio of P squared to M, which is the momentum squared, divided by the mass, minus the expectation value of X times Nambla V. This is the first time derivative, the T, of the expectation value of the product between the position and the momentum of the subatomic particle or the microscopic particle in three-dimensional space. Say that particle could be an electron. And we may have to resolve all of this analysis in some medium, okay? That's it. And thanks for watching. Bye.